You guys all watched the video, right? Right? You all watched the video? Somebody who watched the video and thinks they know what is GD&T, volunteer an answer. What is GD&T? Okay, so GD&T is a TLA, right? What's a TLA? What's a TLA? It's a three-letter abbreviation. You guys go to WPI, right? Where we have IQPs and MQPs. You should be getting good at TLAs by now, right? And so that's actually part of what we're going to talk about today in GD&T is no matter what your career is, no matter what you're doing, there's sort of a language for what you do, right? Right. And so I was in Miami over the weekend, and I'm actually really disappointed, like extremely disappointed. I wanted to be able to come back from Miami and be like, I was in Miami for the weekend, and it's 72 degrees and sunny here. It should be like -10. Then you guys would be impressed that I was in Miami. Nobody cares. But I was there at a conference, and at the conference we were actually talking about marketing and sales. And I told you guys that in my journey to become better at teaching, I started studying things like learning. And then from that, I started studying sales and marketing. And a big part of that was to get better at helping people learn. So I'm at this sales and marketing conference, and one of the things that comes up that confuses customers or students is Technobabble, right? These are the words, the things that we say that when we're talking in-house, in the shop, people know what we mean. So what's a thou? It's Technobabble for machining, right? A thousandth of an inch. What's a tenth? Anybody? You might think so. Who thinks a tenth is a tenth of an inch? A thou is a thousandth of an inch. What's that? You think it's about a tenth of an inch? Raise your hand if first thing comes to mind is tenth of an inch. Right? Raise your mind if you didn't think it would be a tenth of an inch because you knew it was Technobabble. Right? A tenth in CNC machining Technobabble is a tenth of a thou, or a 10,000th of an inch. And so what's 0.0? So 0.1 would be a tenth of an inch, or a tenth of an inch, right? How do we say in Technobabble 0.1, based on what you already know? Based on what we just discussed? Yeah. 100 thou. 0.1 is 100 thou. A tenth is a tenth of a thou. All right, so that's Technobabble CNC machining. When we get to GD&T, another one of these TLAs, it stands for, and let's switch this thing, and it just worked. I love it when the technology just works. I'm looking now for a piece of chalk that's longer than a quarter of an inch. You thought so, but it was 2 pieces of chalk. All right, I guess this one is probably longer than a quarter of an inch, probably double a quarter of an inch. So I'll go with this one, GD&T. Geometric, there's a Technobabble. Oh. See, I'm so excited about the video that I have forgotten how to spell. Let me try one more time. Channeling it. Okay. Metric. Geometric. Who watched the video? What's the next word? Dimensioning. And what's T? Tolerancing. Tolerancing's tough. Some say it's engineering. It lets us make things. Today's haiku. Okay, geometric dimensioning and tolerancing. And so what did he talk about mostly in the video? What did he talk about in the video? What did you learn from the video? One thing you learned. All right, so part of GD&T is who's the professor guy from the Da Vinci Code? Langdon, Professor Langdon. He should be able to help us with the symbology of our GD&T, right? Nobody read the Da Vinci Code? Yeah? Langdon's the guy's name, right? Yeah, he's down at Harvard. Harvard. I don't think he's a real person. Pretty sure he's a fictional character. All right, but symbols. So there are symbols that tell us stuff. What do they tell us? What's the purpose of the symbols? First off, who creates the symbols? Who? Yeah, all right, the programmer at SolidWorks. Right? Because who's had ES1310? Raise your hand. If you be proud, be proud. Stand up if you've had ES1310. Stand up if you had ES1310. What's the course title for ES1310? Intro to Computer-Aided Design? You sure? Really? I'm not sure. That's what it said? Intro to Computer-Aided Design. Okay. What do they teach you in ES1310? You guys are standing, so I can pick on you guys. What do they teach you in ES1310? How to use SolidWorks, okay. What else do they teach you in ES1310? How to combine parts into assembly. What else did you learn in ES1310? How to create drawings. When you're creating a drawing, what's the first thing you choose? You're going to create a drawing. Yes. All right, we're going to choose units. That's probably a good thing to choose. You maybe have chosen the units before you go to make the drawing. Views. Right? Yeah. The sheet size. It's 2 E's. Right? Sheet is 2 E's. Sheet doesn't sound right. Okay, so all right, sheet size. What are your choices for sheet size? A, B, C, and E. Is it something besides A, B, C, and E? What's the sheet size called? ANSIA. That's one of the possible sheet sizes. Is there another possible thing? Yeah. ISO. And is that ABC also? I don't remember. All right, you guys can sit back down. Because this is what I wanted to get out of that. So what are ANSI and ISO? English and metric. I just want to note it's less than 1/4 of an inch now. English, is that true? One of the things that I always try to do when I'm writing stuff on the board in class is to, who's seen the movie Quest for the Holy Grail? Be proud, I want to see your hands. The rest of you haven't seen Quest for the Holy Grail? Yeah, of course. When I was a freshman here, we watched that movie every day for a 7-week term. And we had a copy of the script. So I may have some Grail knowledge that you guys don't have. But the scene where they're in the cave, right, after they've gotten past the rabbit, right? So it's only a rabbit. So the scene where they're in the cave and they're trying to read the stuff that's carved on the wall, right? And one of the knights says, and travel to the castle of right? You guys remember this? It's like, what's the castle of It's like he just stopped writing. And what's the next line? Anybody? Perhaps he was dictating. Like the guy with the stone and the chisel, right? Taking dictation. Yeah, that's like one of the funniest things from the whole movie in my mind. My mind is weird. But when I'm in front of the class, I try to take dictation when I'm writing on the whiteboard. So I try not to judge whether or not your answer is correct or incorrect when I write it on the whiteboard. So is ANSI and ISO the English and metric standards? And if the answer was yes, I wouldn't have made such a big deal out of it. No. But it's not, it was a good guess. It was a guess, right? Yeah. Yeah, it was a guess. It was a good guess. So I will give you a hint. The A in ANSI stands for American. And the I in ISO stands for international. Now, what are ANSI and ISO? Yeah, so this is American National Standard Institute, maybe? I don't know. But the A stands for American. ANSI standards are American standards. International standards, there's probably more than one international standard. But the one most commonly referred to is ISO. Who's driven down the highway and seen a building on the side of the highway that had a banner, like a banner hanging off the side of the building that said ISO 9000 certified? Really? You guys should look at buildings more often because they're all over the place. And so ISO 9000 is actually a standard for how to store documents about your stuff. That's what the standard is. How do you keep track of what you've done? And many, many, many companies will not purchase from your company unless you are ISO 9000 certified. Why might that be? What if the thing you made kills somebody later? Could happen, right? Like on accident. If the thing you made was a gun, then it probably wasn't on accident. But if the thing you made failed and somebody died as a result of it, or some damages happened as a result of it, they want to know, they want to trace back in the manufacturing process why it failed, and are there any other parts in the world that are likely to fail soon, right? Who's ever seen a recall notice on a car or something like that, right? Yeah, this comes from this ISO stuff. We keep track of, so when something fails in the car and it causes this recall requirement, they know which ones are affected because they know which ones have that similar part in it, and that similar design in it. So that's ISO 9000. That's not the one we're talking about today. But it's an example of a standard that you may have seen. So these ANSI A-size drawing, it just tells you the size of the box, right? The size of the drawing. And when you do one of these things, I should check the time. 24, I should check the agenda. Huh. We need to talk faster. So there's stuff down here, right, in your ISO ANSI box, right? There's stuff that goes down there. What's the information that goes down here? Yeah. So yeah, so who we are, the units, the company name, the name of the part, maybe what revision of the drawing it is, things like that. And so they had something like this, 0.00x plus or minus 0.005 maybe, 0.0x plus or minus 0.05, point x plus or minus 0.1, maybe something like that. That goes down right about here in that box. Something like that goes there. What's that called? That's the tolerance block. Oh, just quickly back to ISO and ANSI. The United States is part of ISO. We're a member of ISO. Why do we also have ANSI? Why don't we just do everything in ISO? Any other guess? He said because we're American, that's how we do it. ANSI totally existed before ISO, and so did DIN and J. Is it JIN, the Japanese one, and so did a whole bunch of other all the countries in the world that did manufacturing as a large percentage of their economy had a standards committee like this, had a thing like this, or they would use the DIN standard, or they would use the ANSI standard. So I'm on a couple of U.S. standards committees, and one of the reasons that we continue to exist, and so we meet a couple times a year, and we sit down, and one of the questions that comes up every time we have a meeting is, should we continue to exist? Should we just adopt ISO in this area of standards? And the reason that we have always decided to continue to exist is because we can react faster. So in changing technologies, a smaller organization that and only covering the US can more quickly adapt than the ISO one. Whereas this covers the world, there's more players, there's more influence. And the second reason, so the primary reason is we can meet more frequently, we can adapt more quickly and adjust our standards, although the ones that govern these drawing things haven't changed in a long time. We can do that. The other reason is because the US gets one vote at the ISO meeting. Our vote counts as much as Luxembourg's vote, right? And the other thing, so we want, but we've got a lot more industry and a lot more different segments of our society than Luxembourg does. So, and I hate to pick on Luxembourg. It's a nice place, but it's small, right? What's another small place? Yeah, there's small places out there. All right, but anyway, so that's why there's ISO and ANSI. When you do your drawing, you pick your ANSI tolerance block or your ANSI sheet size, let's say, right? When you pick your ANSI sheet size, that defines how you are supposed to make the symbols. That defines how you're supposed to draw the thing. And so will you go to jail if you violate that? Is it the law? Right? Otherwise, a lot of people would be going to jail if they violated that, right? So the purpose for this standard is so that when you are the designer and he's the manufacturer, you can send him a drawing, and if he doesn't know what one of the symbols is, he can go look up what that symbol means, right? So the purpose of the standard is to facilitate communication. That's the purpose of all standards, is to facilitate communication so that when you get to court and you're suing him because he didn't give you the right parts, and he's gonna say, nope, look at the drawing, I gave you exactly the part you asked for, there's some reference, the judge can figure out who owes who money. All right, so that's why we do this. It facilitates commerce. All right, so in ES 1310, did you guys talk about the tolerance block? He says yes, you must have skipped class that day. In ES 1310, did you talk about the tolerance block? What did they say about the tolerance block? Or they talked about it for that long and you blinked.
I know they talked a little bit about how different parts fit together.
So
You can basically have it where it's loose or tight or thick or like this.
all right, so we've got loose and tight tolerances. Loose and tight tolerances. All right, so we got, oh yeah, the ISO guys chose GPS as their TLA. The U.S. standards group that meets with ISO is called TG 213, so similar to ISO 213. And I was in a TG 213 meeting, and ISO has this overriding standard that says, the first thing it says in the standard is if anywhere on your drawing you specify an ISO thing, your whole drawing must comply to ISO. And so the US was responding to that, because if they're going to say that their standard supersedes our standard, we're going to say that our standard supersedes their standard. It can get a little bit petty like that. But so they've got this GPS standard. And so we wanted to have a cool name like that. And actually, this meeting happened on the WPI campus. And we sat in a room in Cave-In, right? The Cave-In Hall. That's where they do civil engineering. Okay. We sat in a room down there. And we must have sat for like 45 minutes Googling different TLAs to see if it already meant something else, right? Like GPS. Okay, GPS standard, but that's not what I opened up this thing for, right? We got our block. Tolerance block, right? The question was tolerance block. What did they tell you about it? And your answer was loose and tight tolerances. And that's what made me want to open this thing up. Okay. Wrong way. Oh, yeah, okay. So tolerate allows something that's bad, unpleasant, no. All right. So I suppose, so what is a tolerance again? We talked about this earlier in the term. Yep.
Like an allowable error.
Right, I like to say it's how much the designer is willing to let the manufacturer screw up, right? And so we get different dictionary definitions of tolerance. And so I believe, so this is copied out of the Machinery's Handbook, but I believe that in the Machinery's Handbook they copied the ANSI definition. You'll see that sometimes. So it is the allowable deviation from a standard, or the range and variation that is permitted to machining a dimension, a specific dimension. Okay, so that's our tolerance, and this is the standard definition of the tolerance. That's what it means. Why do we need tolerances? Yeah.
Because every part can be machined to the exact
Right, it's not because we screw up, right? It's because machines have certain capacities, right? Anybody know what the smallest increment of motion is in a Haas CNC machine? Somebody shout it out if you know. Yeah. So the smallest programmable increment of measurement in a Haas CNC machine is 0.0001 inches. So a tenth. Anybody know what the advertised repeatability of a Haas CNC machine is? And so when a company, actually, what do we mean by repeatability? No, that's, I mean, it impacts that, but that's not what we mean by it. Yeah, it's not quite accuracy. It's if I move. So what we mean when we say this, the repeatability of the machine is if I move from here to here, and then I move back, and I move back to here again, and I move back, and I move back to here again, and I move back, and I move back to here again. What's the chance of me getting to exactly the same spot again? And so the repeatability of the machine is marketed at about plus or minus 2/10. So we're about plus or minus 2/10, or actually 2/10. So plus or minus 1. Sorry, I said it wrong. So plus or minus 1, it's 2/10. 2/10. So if you had a drawing with a tolerance that said you need to be within plus or minus 0.00001 inches, could you make the parts on that machine? You could try, right? You could try, and some of them would probably be good parts. But you wouldn't know in advance that it was going to be a good part. What would you have to do in order to know in advance that you're going to have a good part? Yeah. You would have to buy a machine tool that has a precision better than this, right? Has a repeatability better than that. If you wanted to reliably make, now, which machine do you think is cheaper? In general, the one that has the, I say lower repeatability, but I mean by lower, I mean closer to like not as good repeatability, right? So the one that has the lower repeatability is going to be cheaper, which means, what does that do to the cost of your part? Yeah. If you have a cheaper machine tool if a cheaper machine tool can make the part, then the part should cost less. If there's time at the end, somebody remind me to tell the funny NASA story about decimal places. But I don't want to take time right now. If there's time at the end, remind me to tell the funny NASA story about decimal places. Okay, so we need tolerances so that we can understand how much we can screw up the part that the designer wants. If we don't have tolerances, we as manufacturers cannot make the part. Or we can hand you the part because we can pick up anything that's on the ground and say, here's your part, if there's no tolerance specified. So as we run the manufacturing labs here at WPI, it's actually interesting. At the very beginning when I took over, I hadn't yet realized how to be a manager. When I realized how to be a manager, I realized that if I was doing all the work, helping all the people and all that stuff, I wasn't doing my job, because my job was to manage the facility and make sure that all the people doing all the helping had all the resources they needed. And so I could help people, and then we'd run out of resources, and I'd have to stop helping people to get more resources. And so it's better for me not to help you, because I'd be the bottleneck in your process now. But what I used to do is I'd run around helping all these people, and I don't know if they were the worst, but very often the graduate students who were getting a graduate degree in mechanical design. Now you'd think these people would know GD&T, right? I've already got a bachelor's degree in something, engineering-ish. Now I'm getting a graduate degree in mechanical design. What do mechanical designers do? They design stuff, right? Not only do that, and once you've designed something, you can't say you've designed it unless you've created the art Unless you've created the drawings and given the and you're able, I suppose you've designed it before you've given the drawings, but you must be able to give the drawings to somebody before you can say you've designed it. Is that true? Do I misunderstand what design means? No, I don't. I don't misunderstand what design means. So when you've designed something, you're able to give somebody else the information with which they could make it. So I'd finally gotten this one kid to understand that some dimensions are more important than other dimensions. And in every design, some dimensions are more important than other dimensions. You believe that? And so the ones that are less important, what should we do with the tolerance? Yeah. We should loosen the tolerance, right? That we started the discussion with loose and tight tolerances. We should loosen up our tolerances, right? And so that means we want to have tolerances with fewer decimal places for the things that are unimportant. And for the things that are important, what should we do with the tolerances? Yeah. There's a few ways to call it out on the drawing. One way is to do this thing in the tolerance block where we do, if it has this many decimal places, it's this tolerance. If it has this many decimal places, it's that tolerance. So one thing, you could put more decimal places. In fact, if you put more decimal places on a drawing, it implies a tighter tolerance. Different funny story. I had a work study who had worked in manufacturing for a while. He gets a drawing from a different graduate student, and he looks at it, and he's all worried, and he comes over to me. And he says, "We can't make this part." I says, "What do you mean? Of course we can make that part." He says, "No, you've toleranced it to 5 nanometers. I said, "Yeah, but he's making a bracket. We can make that part. He just doesn't know how to put the tolerances on here, right? Because he just copied and pasted the dimensions, right? So we want to. So you said be more specific. Who votes we want to make the tolerance tighter? I said we make the tolerance looser if it's not important. Who votes we want to make the tolerance tighter if it's critical? Be proud. Be proud. Be proud. Who didn't vote that way? You didn't vote that way. You didn't vote. Why not? Why not?
If you're too critical, you might affect.
Okay. Or you might not have a machine that can make it. Yeah. You might need a more expensive process to make it. You will certainly need a more. Go ahead. No, I mean if you're the designer and you're choosing the tolerances. Was that clear? Yeah, it was clear. So if you're the designer and you're choosing the tolerances, you may need to have a tighter tolerance. But what you want to do is tolerance on purpose. Remember last week we talked about functional design? We talked about understanding the customer's needs and defining the functions that meet the customer's needs before we do our design, right? And understanding so when we're doing our tolerancing, we want to tolerance correctly, not necessarily tighter. Back to my graduate student kid. So I'd finally gotten him to understand that some things were more important than others. And he came to me and he had this little part, and it was sort of like the size of this piece of chalk. And he's got his drawing. And so down here, he didn't have a tolerance block filled out. But he did specify material, because that's the other thing that you put in that box down here is material. And so he said plastic, aluminum, or some other low density material. I thought, okay. His part was about the size and shape of a cigarette butt. And there were no tolerances called out on his drawing. And he wanted 10 pieces. So I very consciously considered going out and picking up 10 cigarette butts on the ground and saying, here's your parts, to teach him the lesson. But instead I set up the lathe and I machined the parts out of aluminum, and one at a time by hand, because it was only 10 pieces. So I pull the thing out, I measure it, I cut it off. I pull the thing out, I measure it, I cut it off. 10 times I did that, it took about an hour. But he says, okay, great, and if these work, we're going to need 10,000 more. Like, if you told me we were going to want 10,000 more, I would have designed the process already. I wouldn't have made these first 10 by hand. But anyway, said choose the right tolerance. How do we know what tolerance to choose? If you had to pick a tolerance for something, how would you choose? If you had to do it today, what would you do to find out the right number to use? Yeah. We don't have the part yet because you're designing it. But we're going to talk about measuring the parts on Thursday. Yeah. Look at the application. So what does the part have to do? Does it have to interact with something else? So let's say we need to make a hole that a shaft is going to slide through. If we want to design a hole that a shaft can slide through, what do I have to know before I can tell you the dimensions of the hole? We may need to know that, but if it's just going to slide through, so we can dimension it. So I think we're going to be more concerned about the material choices when we look at how much what it has to support. But I think I see what you're going. What do you got? Well, you need to know the variation of the shafts. So if you're purchasing the shaft, say the shaft is a pin of some kind that you're purchasing, you need to know how much those vary. Because if the thing has to fit through the hole, then you certainly need the hole to be bigger than the largest size that shaft is going to be. That makes sense? Now, what else do you have to know? Anything? You need to, yeah, we're going to ignore temperature now. Actually, we use temperature as a tool sometimes when they put aluminum rivets and aluminum airframe parts for airplanes or to put the skin on the airplane. Sometimes you keep the rivets in the freezer. And so when they're in the freezer, they're smaller, right? And so then you put them in the hole, and as they warm up, they expand. So you tolerance the hole so that you just slide it in when it's smaller and it expands. And so you do stuff like that. So when we're doing this, we've got to know what the materials are. We've got to know how loosey-goosey do we want that shaft to be when it's in the hole, right? Do we want it to rattle around in the hole? Do we want to feel pressure or tension when we do it? So these are made your cylinders, right? And you measured your cylinders, most of you, right? And so right now there's a piston in this cylinder, and it can't fall out. Why doesn't it fall? Yeah, not friction. I mean, there's probably a component for friction, but it's not friction. Do it again. Look at my piston in there. Doesn't fall, doesn't fall, doesn't fall. Why didn't it fall? we can ignore that a little bit. So we want to calculate how much force it is before we do it. So yeah, it's going to depend on the elastic modulus, the stress and strain of the two materials, right? And the differences in size. So it's going to depend on how much bigger the shaft is than the hull, and what the elastic modulus of the two things are, and then the friction coefficient between them, because you got a normal force coming from the hole trying to squeeze, right? And so it's going to depend on those things. You might want to go through the other slides in here. It talks about some of that stuff. I try to be funny, and there's a video. See the video, remind me about that. Pits, running sliding pits. We're going to talk about measurement and stuff next Thursday. So Thursday's the next lecture. Tomorrow in Washburn 229, we will be there to answer questions about the group assignment that's due on Friday. Okay, so if you have problems with, yes. Yeah, but I told you guys what it is, right? Yeah, I did. Yeah, the slides. I told you guys what it was. There's no place to submit it. I agree. You can't submit it yet. But it's definitely in the syllabus and on the slides and on the lecture notes from that day where we talked about it. I will have somebody fix the canvas problem. But you should come to class tomorrow prepared to ask questions about that. I will not be prepared to give a lecture tomorrow, but we will be prepared to answer questions about the group assignment. Don't wait until after tomorrow to start the group assignment. So actually, it is in